Hello everyone and welcome back to the Fantastic Academy. This is the second of our two-part series of videos on the ALU processor inside every system. Last episode, we started working on the negator circuit for our ALU as well as the inputs and outputs. In this episode, we covered the multiplexer and how it can be used to finish the wiring of the ALU. Before we continue working on the computer, let's answer last episode's quiz question. Who was the first scientist and mathematician to popularize the usage of binary two's complement in computing? The answer is John von Neumann. John von Neumann was a famous polymath who excelled in many fields and was one of the pioneers in modern computing. Now that we've gotten that out of the way, let's dive in. Now, the need of the hour. How do we get the control signal or subtract signal from our multiplexer to actually translate into choosing what to do? Well, let me introduce the multiplexer. We've touched on multiplexers in previous videos, but this time I'll give them a chance to really shine. A multiplexer takes on conditional input, which are just abbreviated to C, and two other sets of inputs, A and B. Its job, if C is 0, choose A as its output, otherwise choose B as its output. I'll just quickly set them up. There, now that we've set up the multiplexer, let's make the actual circuitry. This is quite simple. All we do is this. For all these B bits, AND them with C. I'm just going to do it right now. And what this does is, essentially, if C is 1, then B will get transferred to the output. But if C is 0, then no matter what B is, it won't come in the output. I'll just intersect these gates here. They may not be that much space, but that's all right. I'll just make the connections quickly. And there we go. We've ANDed the entirety of B with these C in the AND gates. Now, what we can do is slam some OR gates and connect them to the final output. Now, after this, we have to plug in all of these AND outputs to one half of our OR gates. I'll just do that now. And we are done. That was a way messier circuit than I imagined, but we now have this control signal. We can enable these bits, and because C is 0, these bits will show up in the output. Now, whatever I put the B, it won't show up because C is not 1. If I make it 1, then we have the opposite output coming here because that's what's in B. And we've successfully built the 4-bit multiplexer. Now, onto building the ALU and setting up the control flags. There we go, we've set up all the inputs, and now mostly it's smooth sailing and just connecting the circuits we already made. So we have the 4-bit negator, which provides the negated circuits out here. I'll just properly connect it. Now, to decide where to use this negated B line or the normal B line, we go back and add the 4-bit multiplexer, which here, as you can see, is quite massive. we just connect it. And then, because it's in the A line, we have to invert the subtract signal when we input it here. That way, when the subtract signal is on, this will be 0 and we get the output from the A line. Otherwise, we just directly connect the normal unmodified B line into the multiplexer's B line. And we have the output here for the addition phase. Now we can go back and insert the 4-bit adder. Now the issue is that these are interleaved, so the connection will be quite a bit of an issue. I'll just cut here and arrange the wiring. And there we go. That's the ALU fully set up. Now we can do a computation such as, for example, 0, 1, 1, 0 plus 0, 1, 0, 0. That is 6 plus 4. And we get 1, 0, 1, 0. That is 10. 6 plus 4 is 10. Yay! By enabling subtract, we can get to see that 6 minus 4 is 0, 0, 1, 0, 2. 6 minus 4 is 2. It works, yay! Now we just have to include the extra information flag signals that I mentioned. So on the output, we can just take the C out from the final carry out. But I want to add a few more flags. In fact, I'll just add one more, the 0 flag, which will be on if and only if all of these are equal to 0. Now, luckily, there's quite a convenient gate for that, the NOR gate, which only turns on if both of the inputs are off. So I can NOR both of these together. Then I can separately NOR these together. And finally, I can take an AND gate, which just perfectly fits in between the two wires that are carrying O2 and O3. Now it seems here that I've put a normal OR gate instead of a NOR gate, but that's easy to rectify. And there we go. The output here will be our 0 flag. And there we go. That's the ALU finish. The ultimate climax of all these episodes, we have a computer running on my computer that can fully think, do computations, output flags, add and subtract using a multiplexer. It's taken a long time of work to reach here, from having flip-flops to 2's complement in one of our first episodes in this series, but we finally made it here. Now, I'll pass it back on to Canva Ayush for the ending. Thanks for that, Computer Ayush. So, in summary, what did we do today? We built a 4-bit multiplexer and we finished wiring up the ALU with the help of the multiplexer. We discussed control flags such as the 0 and carry output and added those to our ALU. Now let's end this video on with a light-hearted note with a quiz question. What is the equivalent of the ALU to process decimal or floating point numbers in your system? Tell me the answer and I'll see you on the next episode of the Fantastic Academy. Bye!